In addition to the food processing plant example, the whole use, the on-farm practices that are becoming mainstream in food production. Large numbers of animals are being raised on a small amount of land. These are called concentrated animal feeding operations. You have thousands and thousands and thousands of cattle going to slaughter on a very small area of land. There is a lot of fecal material. There is a lot of exposure. It's fertile breeding ground for pathogens. You look at again, this centralized processing, you have huge fields of spinach and lettuce in Salinas Valley, California, sitting adjacent to dairy farms. And when you have wet seasons, you get a lot of runoff. And if you don't have sufficient barriers or distance between runoff from dairy farms right into those fields.
That begs the question, is there value in rethinking the whole system in terms of a more regional food production on a smaller scale with more regional distribution and a shorter distribution chain and basically fresher food, more local food? Is the time coming where we need to think about that, at least in terms of some foods that maybe are more amenable to a local food production? We need to be thinking about those possibilities.
As we've heard, large-scale production and processing has the potential to create far-reaching problems. But food that is locally grown is not immune to the issues of foodborne illness. A critical challenge facing scientists today is how to detect foodborne pathogens accurately and timely before they enter the food supply.
If you're trying to find a pathogen in association with a food product, you're really doing the needle in a haystack approach.
So you really need a technology that has the ability to pick out the pathogens that may be mixed in with the harmless bacterial flora. And we showed we could do that with infrared spectroscopy. Visible spectrum is approximately 0.4 to 0.7 microns in wavelength. For the research that we're doing, we operate at wavelengths between 2.5 microns and 25 microns. So this is our Fourier transform infrared spectrometer. And inside here there's a light source that generates light from 2.5 to 25 microns, and it's piped into this infrared microscope that uses mirrors to focus the light instead of lenses that you have in a typical microscope. And it focuses the light down onto a sample that we placed here on a slide. And then the light is reflected off the top surface of the slide after various wavelengths are absorbed or not absorbed, depending on what's in the sample. And the light comes back in through the microscope, back into the spectrometer. And the spectrometer measures the absorbance as a function of the wavelength of light. Every molecule has unique infrared spectral signature. There's certain wavelengths of light that a molecule likes to absorb and certain wavelengths it doesn't like to absorb. So one of the hardest things to do now in testing is to tell the difference at the strain level between, these harmless E. coli and the harmful E. coli. We actually were able to show that we could tell apart two different strains of E. coli 100% of the time. And that's important for food safety because the vast majority of E. coli strains are harmless bacteria, even beneficial and aid in the digestion process. But some strains have mutated and acquired pathogenicity, and there's at least 100 different strains of pathogenic E. coli. Each bacterial species and even strains produce slightly different chemicals, and they certainly have different DNA and RNA, and we can sense those chemical differences with infrared light. We need to collect a lot of these spectra for all the different organisms that we want to identify, and then it's my job to write an algorithm that will take an unknown spectra and interpret it and say, yes, Listeria is present, or Salmonella is present, or E. coli is present. But for me to write those algorithms, I need to collect the data and understand what the natural variation of the spectral signature is for these different organisms. The food also contributes to the infrared spectral signature too. So we need to understand, what the spectrum of the food looks like as well. After we've collected the spectral signature of the sample, all the different molecules in the sample contribute to that spectra, and we can determine the chemistry of the sample from that spectra. But one of the advantages of infrared spectroscopy is we can give you a real-time test result, so you can tell immediately if there's contamination in the food or not.
Infrared technology is a promising method for real-time pathogen detection. Back at Jane Hill's lab, she describes another promising approach using a mass spectrometer.
The other area that we work on is trying to rapidly detect pathogens, and we're able to look essentially for a fingerprint of a bug by looking at the volatiles that it produces. Using a piece of equipment called a mass spectrometer, we're able to charge up some molecules that are produced by a bacterium, so a gaseous cloud of molecules. When we exhale, we produce a whole lot of different gases in that exhalation, and bacteria are very similar.
So we grow the bacteria in this incubator. We grow it in an airtight manner so that we've trapped the gases that the bacteria have produced, and we flow the gas that the bacterium has produced into the mass spectrometer.
We can send them into our system. The system imparts charge onto those molecules, and then it's sucked into our mass spectrometer, where we're able to detect the mass and the identity of those compounds, to essentially sniff bacteria. And when we sniff bacteria, they're producing particular types of compounds that we can measure, and those compounds differ from one bacterium to another. So they're like a fingerprint, so we're looking for a bacterial fingerprint. So an E. coli will produce different volatile molecules, some different volatile molecules than, say, a Salmonella, than a Campylobacter, than a Listeria. And we're at the beginning of that technology. The main disadvantage working with a mass spectrometer is that the piece of equipment itself is very expensive. In all other regards, there's no sample preparation, it's very rapid, the results are reliable, it excels above pretty much any other technology, but the initial cost is the thing that's the kicker.
Our global food production infrastructure is complex, and real-time detection does not exist. Currently, efforts are focused solely on tracking symptoms and identifying trends, and a federal surveillance system is in place to help anticipate outbreaks.
The Centers for Disease Control has set up a network called FoodNet, and what they do is do surveillance of a number of selected sites in the United States, and so they're following who's getting admitted to the hospital. And so through FoodNet, we've got an idea of what is going on out in the population compared with the baseline that was established in 1996. And so all state public health labs are now connected to the Centers for Disease Control, and they all use this technology, and they have a system called PulseNet. And so when one of the FoodNet reporting sites sees clusters of cases, they start to suspect maybe a large-scale foodborne disease outbreaks. And most of the time when these outbreaks are investigated, you can go right back to that food and find that same genetic fingerprint, and that's the proof of evidence. And that's why it's such a complicated science of putting this all together. And because it's so complicated, most foodborne disease outbreaks go totally undiagnosed. And so the statistics that we have grossly underrepresent what's really going on out there.
One of the big areas for tackling foodborne illness is actually public education, because even if a ground beef or poultry or another food item is contaminated, raw cookie dough for example, if you handle the food properly and cook it to the appropriate temperature to kill any bacteria that are present, it won't make you sick. Don't cross-contaminate cutting utensils and cutting boards in the kitchen if you're chopping raw poultry and then chopping vegetables. So those basic things can really prevent foodborne illness.
The majority of the food industry is 100% totally committed to food safety, but the 1% bad actors drag the whole industry down. But I also think that consumers play a great role in having choice. And I think, again, in Vermont, what's very exciting is seeing the whole local food movement. Where's my food coming from?
The thing with regional food is the distribution tends to be smaller. That's the whole idea. It's regional. And so if there is a contamination problem, it might impact fewer people. It might not turn into a national outbreak.
And the nice thing about a local food movement, it does give that choice. It also is a wonderful educational tool to more closely connect people to where their sources of food are coming from. There's a certain segment of our population that really doesn't care. I mean, they care about feeding hungry kids and having enough to eat, and so they're making assumptions that their food is safe. And I hope those assumptions always hold true. But then there are others who've decided to become more empowered that I want to know, show me the field, show me the place where this food production is taking place. And I think it's exciting because I don't ever want to live in a society where we're so centralized that we become so vulnerable to problems. When you think about how much food moves around the world on a daily basis, it's truly mind-boggling. And the number of people getting sick, while we may really want to reduce that significantly, it's just a little amazing to me what we're able to do without incident. And the more of that kind of work we can do and the less reading about these outbreaks would make us all happy.
Fortunately, Vermont scientists are developing strategies to understand food pathogens and limit our exposure to outbreaks. The Center for Disease Control and the Food and Drug Administration have tracking systems in place to recognize when outbreaks occur and to order recalls when necessary. It's critical to educate yourself and your family on how best to prepare food to limit your exposure to foodborne illness. Once again, we're reminded that research science affects our lives in places and contexts we may rarely consider. I'm Amy Seidel. Join me next time for more Emerging Science.